This image shows electrical data during an unfortunate fatality, arc flash incident. This relay was supposed to send a trip signal to the breaker to remove the arc flash incident and prevent a significant injury or fatality. It did not. To be exact, the trip signal came after an eternity. A worker caught on fire in front of their co-workers. The worker was rushed to the hospital and was later pronounced dead. The worker left one spouse and 2 kids, among them a newborn baby. What was a significant contributing factor to this tragic event? Inaccurate arc flash and electrical studies. Let me repeat it. Inaccurate arc flash and electrical studies. It is not a one-off event I am showing you. I reviewed 21 electrical facilities in USA and the same story with arc flash and electrical studies. 10 deaths, significant equipment failures, miscoordination leading to financial losses, electrical fires, wind farm unable to run at the maximum design. I had to redo 20,000 arc flash labels. In some facility, some engineer and technician told me they had a suspicion something was not correct. They just couldn't find the rules. I asked what made them suspicious. Some answers. We hired 3 engineering firms to do arc flash studies within 3 months for the same facility. Their results were all significantly different. Some sites had no idea their study was so incorrect. Look, 250 calories. Incredible, isn't it? I actually had to sit with several engineers and show how to detect correct or incorrect arc flash study using real-life data. Let's analyze this event and discuss the drastic errors. The top chart is current as indicated by the unit and the legend. The middle one is voltages. The bottom is digital chart. You can see 52A is on and the trip signal is off. 52A on means breaker is closed. After 25 cycles, the breaker is still closed and the trip is not sent. On the top right, there is a summary of the event. It shows the name of the relay, 52-F. It also shows the phase fault type, line-to-line AB fault. The peak current magnitude during this event is here. IA is around 5,000 amps, IB is around 4,000 amps. The other currents are here. The phase fault type is sometimes not correct as it is difficult for the relay to analyze evolving fault. When we deal with current and voltages, we mostly talk in terms of RMS, which means root mean square. It's also called magnitude or intensity, same thing. I am removing the instantaneous value and I am placing the magnitude values. This red dotted line is the instant when the fault occurred. On the left side, it is the region before the fault. Before the fault, all phases current were equal to 15 amps. Same with voltages 19.9 kV. We are talking VA, VB, and VC. There are phase voltages, not line voltages. This is the simulation model of the facility. The current reading of the relay is here. For more info, 215 amp is actually not the full load amp of that feeder. The full load amp is 431.8 amps. Some equipment was down at the time. That is why it is running at 215 amps, 50% of full load amps. 52F relay is here on the simulation. Back to real life event. We are now scrolling until we hit the fault and we see current jumping to close to 5,000 amps for A and B current. Voltage dropped to 15 and 12 kV. The fault is still present. Currents on A and B stayed high and voltage still lower than nominal. This event ended because of memory limitation of the relay event and a new event of the same fault starts. Before we close this event to go to the next one, pay attention to the time so you can see the coherence across multiple events within milliseconds. Event 1 time starts 8 hours, 20 minutes, 23 seconds, and 941 milliseconds. Event number 2. Look at the time, 8 hours, 20 minutes, 24 seconds, 712 milliseconds. That's 771 milliseconds after event 1 time starts. 771 milliseconds is 46 cycles. Once again, we can see the instantaneous sine wave value. On the right, you have event summary with the same relay 52-F. The event type is now CA ground, phase to phase to ground. It is no longer AB face-to-face fault as shown in event 1. Remember, this event type is sometimes incorrect as evolving faults are a challenge for the relay. Peak values of current are here. Unlike in event 1 where IC was 40 M, IC is now 3300 amps. I am removing the sine wave and now deal with magnitudes or RMS or intensities. IA fluctuates around 5000 amps and IC fluctuates around 4000 amps. IB is around 2000 amps. I insert a white line here called V nominal, which is 19.99 kVA. V nominal is the nominal voltage of the system. VA, VB, and VC are much below V nominal. VA is the lower one at 13 kV. The breaker 52A is still energized. The trip has not been sent. 25 cycles after the second event, fault is still there. And now the fault has evolved from a phase-to-phase to potentially a phase-to-phase ground, or maybe even a 3-phase fault. Event number 3, it is still a phase-to-phase ground, but not CA ground, it is now AB ground. Look at the peak current magnitudes. We could argue we have a 3-phase fault. Let me insert the magnitude data. We see current are respectively 5000, 4000, and 3000 amps. Voltages are 13, 12, and 16 kV. Now, finally, we can see the trip here at the end. That red trip block color is showing up here. The breaker is still on because it is 3-cycle breakers. Event number 4, breaker is finally off here. As you can see, currents read all zeros and voltages are back to nominal conditions. Fault was removed at time here, which is 8 hours, 20 minutes, 25 seconds, 671 milliseconds. If you remember, the incident started with event number 1 at 8 hours, 20 minutes, 23 seconds, 941 milliseconds. When we calculate the durations, end time minus start time, we get 1.73 seconds, which is 103.8 cycles, about 104. It took 104 cycles, ridiculous. IEEE Birth Book, a prominent guidebook on protection, states it should take 1 to 3 cycles for relay to send signals when the fault is at the primary zone. This relay took 101 cycles before sending a trip signal. This relay was 101 times slower than general guidance fastest case scenario. A NAC flash fault occurred at the primary zone of this relay. The fault jammed 13 per unit. It took 101 cycles for the relay to send the trip. Ridiculous, mind-boggling. Are we going to blame any equipment? Are we going to blame the technician or engineer who programmed the relay? Are we going to blame unknown reason that we can't easily prove nor disprove? That is typically what we are accustomed to do. Not so fast. We have all the data to prove that the issue was somewhere else. How many calories were released during this fatality? I use ETAP Arc Flash Calculator tool and input all the data here. We select the right module arc fault, not AC arc flash, arc fault since it's higher than 15 kV. The right method, 3-phase, line to line to line, fault type. Input parameter, we got a voltage line to line, the voltage fault current. Conductor gap working distance, then we got a reflectivity coefficient A and K. And we have the fault clearing time, which is 1.73. After finishing inputting all those values at the right data field, voltages, voltage fault current, conductor gap, and all the reflexivity coefficients, look at the result, 45.26 calories. Much higher than what the existing lab stated, that it should have been less than 12 calories. The software also stated it should have been less than 12 calories. Look at the arcing current, matches what the actual really reads. That is the issue, right? The pickup point for their labels did not occur when the actual arc flash fault happened. This is the existing model of the facility they used to produce the arc flash labels. I will run the study with identical conditions from the incident. The software said 8,000 amps. The incident occurred and it was not even close to 8,000 amps. How do you know you are correct when performing electrical studies? If you are a reviewer, how do you know your review is accurate? It comes down to one thing. Almost everyone thinks that when your electrical drawings and field data are correct and that those data are correctly inputted into the software, the result will be right. That is an incorrect statement, an incorrect conclusion. Power simulation software are not computer science programming software such as Java, C++, C#, Python, etc. In C++, you must input or type everything for your Hello World program to compile and work. In the power system simulation, you do not have to input or type every data for your program to compile and run. That's the big issue. Critical parameters and options come default. They may not be the right values for your power system. Number 2, critical scenario case must be built properly. If you don't do them properly, your program will still work. 3, some data you have to input may not show on the nameplate or electrical drawings, and the software default data may not be applicable for your system. That's the reason why almost every time when I compare simulation with real incident, there was a significant difference. Look at what I did for this issue. I mostly checked the data discussed on 1, 2, and 3. I did this in front of the engineers. When I was ready, I called everyone in the room, including electricians, supervisors, managers, because I wanted to witness their reactions. I opened the model, click on Arc Flash, select, and run. Look at this. $4,500 amps in the software. The reader reads 5,000 amps. We have a match. There was a long silence in the room. It was priceless. The incident was not removed fast enough because the relay was programmed to trip on instantaneous at current 8,000 amps or above. It should have been 5,000 amps. If you perform electrical studies solely based on electrical drawings and nameplate data, your results are most likely inaccurate. If you review electrical studies solely based on verifying if the data input match the data in your software and nameplate, your review is most likely flawed. There is one exception to this conclusion. If you have a low complexity power scheme, you will have no issue. Unfortunately, mediocrity is the Achilles heel of this discipline. In most cases, whether a study is accurate or not, the electrical facility will still run. Thereby, we have limited to no accountability in the accuracy of the results. The mindset and culture are so incorrect. Garbage in, garbage out does not mean not garbage in, not garbage out. Data input correctness is necessary, but not sufficient to determine accuracy. Benchmarking simulation results with real incident is sufficient. The million-dollar question is, how can I benchmark result of a simulation before approving it? Well, you have to acquire new skills. You have to train. 80% of electrical incidents are investigated had the same cause or significant factor: engineering errors, incorrect power studies. I am Thierry Epasa, and I approve this message.